Hello friend, welcome back. Myself Dr. Keshao Mahale. Today we are going to discuss the remaining part of Stereochemistry chapter. So in this lecture we are going to discuss the representation of organic molecule in stereochemistry. There are four methods. These four methods now we are discussing here. The first method is wedge dotted formula. Wedge dotted formula is given for the tetrahedral carbon atom. This is the parallel carbon atom in which we are drawing here the tetrahedral structure. See, these are the four type of bond which are discussing by us in last lecture. So, see, this is the hydrogen here, this is the methyl group here, this is chlorine here, and this is the hydrogen group here. Friend, see in this formula, these two bonds are the normal bond which shows these two groups are present on the plane. This is wedge line, wedge formula. This show us this hydrogen group is in front of the plane or above the plane. And the dotted line show us the group present on behind the plane or below the plane. What is meant by this? In front of the plane or above the plane, behind the plane or below the plane. See, this is the tetrahedral molecule in which we can discuss all three types of bonding which I have drawn here. See, if this is the tetrahedral molecule and I hold here the tetrahedral carbon atom, which is a chiral carbon atom here, which having four different groups. Then, see here, if we pass the plane through this green and this white group, if we consider here this hand is the plane, then you can see here one group is present in front of the plane and one group present behind of the plane. See here, this is the plane in which one group is in front of the plane, one group is behind the plane, and two groups present on the plane. So therefore, we can see here these two groups present on the plane, these two groups present on the plane. One group is in front of the plane. See, this group is in front of the plane and the remaining one group is behind the plane. So this group is behind the plane, which is shown here by the dotted line. So this is three-dimensional model. But when we write, when we draw on the board or on the page, then it will be the two-dimensional. So in two-dimensional representation, we use this wedge line and the dotted line. For this structure, we have to keep in mind one thing: the group present on the plane shown by the normal line, the group present in front of the plane and the group present behind the plane shown by the dotted line. Friend, see here, if we rotate this structure in such a way that our plane will be the horizontal plane. See, this is the horizontal plane. We can see here these two groups are on the plane, which is shown by the normal line. One group is above the plane, which is shown by the wedge line, and one group is the below the plane, which is shown by the dotted line. So this is a wedge dotted formula, and it is very important in stereochemistry. Now, our second formula is Fischer projection formula. Second one is the Fischer projection formula. Fischer projection formula is used for showing the stereochemistry, for showing the configuration on the adjacent carbon atom. So here are some points that we have to remember. First things, there is a vertical line. Firstly, we have to draw here the vertical line. Vertical line shows the longest chain in that organic compound. Then after the horizontal line, there are some horizontal line which are equal to the chiral carbon atom. The third point is Fischer projection formula is always in eclipse form, and the fourth point is the most oxidized group is on topmost position. These are the very important point when we drawing the Fischer projection formula of any structure. See, the first one is the vertical line shows the longest chain. The horizontal line are equal to the chiral carbon atom, and Fischer projection formula is always in eclipse form, and the most oxidized group in Fischer projection formula is always on the topmost position. For understanding this Fischer projection formula, we have taken here the example 2,3-dibromobutane. See here, this is the structure of 2,3-dibromobutane, CH3, CHBr, CHBr, and CH3. If we numbering the carbon chain, see this is 1, 2, 3, and 4. This is 2,3-dibromobutane compound, and the longest chain is the chain which having 4 carbon atom. Therefore, according to our first point, the vertical line shows the longest chain. Therefore, if we draw here the vertical line, see this is the vertical line, and vertical line shows the longest chain. The horizontal line is equal to the chiral carbon atom. Firstly, we have to identify the chiral carbon atom. See here in this structure, carbon number 2 and carbon number 3 are the chiral carbon atom. Therefore, there are 2 chiral carbon atom, and hence the chiral carbon atom equal to the number of horizontal line, and hence we have drawn here the 2 horizontal line. Then after, see here, the Fischer projection formula is always in eclipse form. We have to remember this point when you convert the Fischer projection formula in a Sawhorse projection formula or Newman projection formula, and the most oxidized group is it's on the topmost position. See here, the carbon number 3 and carbon number 4 are the CS3, and hence and this structure is the symmetrical. Therefore, we can start from here. See, this is the CS3 here. This is hydrogen here. This is bromine here. This is again hydrogen here, and this is again bromine here, and the last one is CH3. So this is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So we can say that this is Fischer projection formula of 2,3-dibromo-butane. So one question is always asked: draw the Fischer projection formula of so and so compound. So therefore, we have to drawing the Fischer projection formula in such a way. One another question is asked always in a competitive exam. That question is nomenclature of Fischer projection formula. You have to given some Fischer projection formula structure and asking one question. Write the name of following compound. So in this point, we can write here the nomenclature in Fischer projection formula or nomenclature of Fischer projection formula. There are four types of compound named by four systems. Therefore, firstly, I draw here the four structure which having two chiral carbon atom. See here, on vertical line, if the groups are same, and on the right hand side and left hand side if the group are same. See, this is B here, this is B here, this is C, and this is C. We have to keep in mind the structure of this type. On the vertical line, if two groups are the same. On the right hand side, if two groups are the same, and on the left hand side, if two groups are the same, then this structure is called as a mesostructure, and the name of compound will start from the meso. Now, in second type of the structure, if the group present on vertical line are same, the group present on right hand side are different, and left hand side are also different. Therefore, we can see here this C group is cross here and D group is cross here. Then this structure is called as a DL pair. Then, in a next structure, if the group present on vertical line are different and group present on the right hand side and left hand side are the same, then this is called as a trio structure. And in last structure, if the group present on vertical line are different and the group present on right hand side and the left hand side are also different, then this is called as the erythrodes. So these are the nomenclature in Fischer projection formula. Our next presentation, next type of formula is the Sawhorse projection formula. This is third system to represent the organic molecule in stereochemistry. Sawhorse projection formula. Sawhorse formula is also repeated the stereochemistry on the adjacent carbon atom. So we can draw here the structure of butane by Sawhorse formula. The structure of N-butane. See, this is the N-butane. If we numbering the carbon atom, this is 1, 2, 3 and 4. The adjacent two carbon atom here are carbon number 2 and carbon number 3, on which we can show the stereochemistry. So firstly, see if this is the carbon number 2, in which we can say here there are 4 groups. The one group is the CH3 and there are 2 hydrogen and one group is the ethyl group. So therefore we can draw the structure like this. See, this is the carbon number 2 here. This is CH3 here. These are the 2 hydrogen. So we can write here this is carbon number 1 which having the CH3 group, carbon number 2 which having the 2 hydrogen and 1 CH3 group. This is carbon number 3 which having 1 CH3 group and again 2 hydrogen. See, this is carbon number 3 and this is the carbon number 4. See here, this is Sawhorse formula. We can see here, if the carbon that I hold here is the carbon number 1, this is the CH3 group, this is carbon number 1, carbon number 2, carbon number 3 and this is carbon number 4. If the dihedral angle between two CH3 group, that is the same group. Dihedral angle between the two CH3 groups, see this is the dihedral angle. So the angle between the same group is called as the dihedral angle. If the dihedral angle between two CH3 group is the 0, the dihedral angle between two CH3 group is the 0, then this structure is known as Eclipsed structure, Eclipsed Sawhorse formula. So dihedral angle is denoted by this notation. Dihedral angle is 0 degree. Then this is the Eclipsed structure. If we rotate this structure by 60 degree, so see here, this is carbon number 2 and this is carbon number 3. If you rotate the structure through this single bond, see by the 60 degree, if you rotate the structure through the single bond by the 60 degree, then structure will appear like this. The dihedral angle between these two CH3 is now 60 degree and this structure is known as a gauge structure. The position of second carbon is the same here. This is CH3, this is hydrogen, and now this is the CH3 here, this is hydrogen here, this is hydrogen here, and dihedral angle between two CH3 is the 60 degree. Again, when we rotate carbon-carbon single bond by 60 degree, see here, if you rotate again carbon-carbon single bond by 60 degree, then the dihedral angle between two CH3 is the 120 degree and it will be this structure is known as the partially eclipsed structure. The structure will be like this. The configuration at carbon number 1 is the same here. This is CH3, this is hydrogen, this is CH3 here, this is hydrogen here, this is hydrogen here. And finally, we can rotate here again 60 degree. See here, in this structure, when we rotate this by again 60 degree, then we can say that the dihedral angle between the CH3 group and other CH3 group is now 180, and to this position when the dihedral angle between the same group is 60°, then this structure is known as the stagger structure, which is very stable structure. See, in this structure, the dihedral angle is 180°, and this is the stagger structure. Stagger form. Now this is 1, 2, 3, and 4. The dihedral angle is 120, and this is the partially eclipsed. Partially staggered. So these are all the Sawhorse projection formula. I have told you when Sawhorse projection formula is used. Sawhorse projection formula is used at that time when you want to show the stereochemistry at the adjacent carbon atom. Stereochemistry at the adjacent carbon atom. So for example, we are taking here the N-butane. So this is the N-butane, because if you consider this red group is the CH3, this red group is the CH3. See, this is CH3, CH2, CH2, CH3, and this is the carbon number 1, 2, 3, and 4. See, I have told you when the dihedral angle between these two groups is 0, then this is called as eclipsed structure. And eclipsed structure is a very unstable structure. When the dihedral angle means there is a carbon-carbon rotation, and when carbon-carbon rotation is here, when there is rotation of carbon-carbon single bond by the 60°, then the dihedral angle between these two groups, this 2 methyl group, is 60°, and we got here the Gauss structure. Again, when there is rotation of carbon-carbon single bond by 60°, means the dihedral angle between these two CH group will be 120°, and the structure is partial Gauss structure. And finally, when you rotate carbon-carbon single bond by 60°, then the dihedral angle between these two CH group will be 180°. Now we can see here the CH3 group on the carbon number 2. And the CH3 group on the carbon number 3 are apart from each other, and hence there is a very less steric hindrance, and the structure will be more stable. So therefore we can see here the CH3 group. See, this CH3 group and this CH3 group are very apart from each other, and therefore there is a very less steric hindrance. And you can say that when dihedral angle is 180°, the structure is called as stagger structure, and it will be the very stable structure. Friend, now we are discussing here the fourth type of formula, Newman projection formula. Newman projection formula is also shown for the stereochemistry on the adjacent carbon atom. Again we have take the example N-butane. See here, this is Sawhorse projection formula of N-butane. If we see the model here, see, the viewer is from here. If this is the front carbon atom that appears to the viewer or observer, and this is the rear carbon atom. See, this front carbon atom, if we numbering the carbon atom, this is carbon number 1, carbon number 2, carbon number 3 and carbon number 4. If viewer or observer is from this side, then the observer first see this carbon number 2, means this is front carbon atom and this is the rear carbon atom. So we consider here carbon number 2 is front carbon atom and carbon number 3 is the rear carbon atom. Then in Newman projection formula we can write here, see, there are 2 points we have to remember. In first point, the front carbon atom is shown by the dot. Front carbon atom is shown by the dot, and rear carbon atom, that is back carbon atom, shown by the circle. So therefore we can convert this Sawhorse projection formula in the Newman projection formula. We have already discussed that this carbon number 2 is the front carbon atom and carbon number 3 is the rear carbon atom to the observer. See, this is the model. If you see here, this is front carbon atom and this is rear carbon atom. I have told you the front carbon atom is denoted by the dot. So this front carbon atom having one CH3 group that I have drawn here. This is one CH3 group. This is one hydrogen to the right hand side. This is one hydrogen to the right hand side. This is another hydrogen to the left hand side. This is front carbon. Now rear carbon atom is denoted by the circle. This is rear carbon atom which is denoted by the circle. And rear carbon atom, see here, the rear carbon atom having here the CH3, one CH3 group. This is another hydrogen group here, and this is the second hydrogen here. So this formula is known as the Newman projection formula, and we can see here the dihedral angle between these two groups. Two same group, ethyl group is the 0, the dihedral angle Q is equal to 0 here, 0 degree, therefore this is eclipse conformation. When we rotate this carbon-carbon single bond by 180 degree, see here, if this is the carbon-carbon single bond, and if you rotate from 1 degree, then you got here the stagger structure which is already discussed by us in last time, that is the Sawhorse projection formula. So therefore we have to rotate here this CH to the 180 degree. So our front carbon atom which is denoted by the dot is the same here. See, this is CH3 here, this is hydrogen here, this is hydrogen here. Now this is rear carbon atom which is denoted by the circle, and which having, see, this CH3 comes here, which having 180 degree, one hydrogen is here and another hydrogen is here. Now dihedral angle is 180 degree, therefore this is stagger form. Or you can say this is the stagger conformation. Here is the dihedral angle is 0. So this is Newman projection formula, which is very simple to draw. So again, I told you there are 2 points. The front carbon atom is denoted by the dot, and rear carbon atom is denoted by the circle. We can convert the Sawhorse projection formula in Newman projection formula. First we have to observe the front carbon atom, and by observing the front carbon atom, we have to draw first the stereochemistry of first carbon atom. See, This is the CH3 to the vertical line, and this hydrogen is toward the right hand side, another hydrogen to the left hand side, and then after on the rear carbon atom there is one CH3 which is draw here, one hydrogen atom is draw here, and another hydrogen is drawn at the left hand side. So we can see here there is 0 degree dihedral angle, therefore this is called as eclipsed Newman projection formula. And when you rotate carbon-carbon single bond, when you rotate this carbon-carbon single bond by 180 degree, so therefore this CH3 comes opposite to the first earlier CH3, and dihedral angle will be 180, and hence in this structure we can see here the dihedral angle between this CH3 and this CH3 is 180 degree, and therefore this is called as staggered Newman projection formula. So friend, these are the 4 methods for representation of organic molecule in stereochemistry. Now in next lecture we have to discuss how to convert Fischer projection formula in the Newman projection formula, or Sawhorse projection formula in the Newman projection formula, or Newman projection formula in the Fischer projection formula. So therefore we have to firstly keep in mind, if you want to understand the stereochemistry very deeply, then we have to firstly know how to draw the organic molecule in all these formula. So thank you.